Hello, everybody. So this is a series of videos for the final or the practice final for your Calculus 1 class. I want to first congratulate you for coming this far. This has been your first semester calculus class, and it's been long and hard and rigorous. And so it's great that you have come this far, and now you are preparing yourself to take your final exam. All right. So the final exam, practice exam, is available in Canvas, and I have already provided an answer key in written form. But these videos will go over how to solve each problem step by step. And so this will be sort of an additional resource for you as you prepare yourself for the final exam. All right, so let's get started with these problems as you study for your final. All right. So the first thing I want to do is to make sure you pay attention to page 1 of my document preparing or preparation for the final exam in Math 211, your first calculus class. All right, so make sure you know how to do these things. This is a summary of what you will be expected to know and to be able to do on your final exam. I know it's a lot, but this is your first semester calculus. There are some things that you do not have to study for as you prepare for the final, and those are listed. These are sort of, these are not unimportant, but these are not as important as these other topics and skills that you need to demonstrate on your final. And then there's some information on the format of the final. And as I state at the bottom of page 1, the best way to prepare for this final is to try the following exercises. And of course, there are 2 pages of exercises. I suggest that you do all of these and correct your answers by your answer key or by these videos. Now, there are 22 questions here, and I will do in part, I will do, maybe I'll make, I don't know, 4 or 5 of these parts as I divide up the videos into smaller parts. And so I will try to do these problems one by one. All right, let's get started. Hold on, it's coming. Okay, don't leave. All right, the first question that has several parts. Actually, that's not the way it is, isn't it? Okay, so this is number 2 here. All right, the first set of questions has to do with infinite limits, right? See that? Or limit at infinity, I should say. So when you have a rational function, which is a polynomial over a polynomial, you look at and pay attention to the degrees. The degree here is 1, the degree here is 2. You know that the second degree polynomial in the bottom grows much faster than the one on the top as x goes to infinity. So this will just become 0. Now, there is a more technical explanation. You can divide each of these terms by, let's say, x. All right, and then you see that the top will just become 3, and then the denominator will still go to infinity. And so, you know, a finite number divided by a quantity that goes to infinity is going to approach 0. So the limit is equal to 0. So that shouldn't be too bad. For the second one, the notice here, the degrees are the same. So the degree is 1 here, degree is 1. And so for this one, maybe it helps to see what I was just talking about. Just divide every term on the top and bottom by x. And what happens? As x approaches infinity, this will go to 0. This will go to 0. This is actually 3 for all x, right? And this is also 2 for all x. And so this will be simply the limit as x approaches infinity of 3 over 2. Well, 3 over 2 is a constant, so the answer is 3 over 2. No problem here. All right, so the part C, you have a denominator, degree 1, numerator, degree 2. Okay, this goes to infinity much faster. All right, so it's exactly the opposite of what happened here. If the top is going to infinity, and again, you can divide each of these by x, and you will see that the denominator will approach 2, but the numerator still goes to infinity. So this will be positive infinity. right? Now, technically, we say when this happens, we say the limit is infinity, or you say it's an infinite limit. But technically, you can also say the limit does not exist because it's not a real number. Okay, notice here, infinity is not a real number, and it'll never be. But you would probably be okay in saying that the limit is at infinity, or limit at infinity is positive infinity. Okay, so number 2, I need to change these. These are A, B, C, parts A, B, C of the second question. The first one, limit as x approaches infinity of sine of x over x. Now notice here, this, what I can say is that sine of x is limited in its domain, right? It's never going to be less than -1, and it's not going to be bigger than +1. So what happens is this oscillates between +1 and -1, but this goes to infinity, right? So we're talking when x is like a million, okay, this will be a number that is very close to 1 over, or -1 over a million, which is very, very, very close to 0. So as x approaches infinity, this will approach 0. Okay, so that's part A. Part B, as x approaches 0, this is the first time x, well, these two, x is approaching 0. Everything else so far, x was approaching infinity. But when x approaches 0, then of course the argument we use here will not apply. And so what is the answer here? Well, for this one, you do have to know and remember what we did back in chapter 2 or something, right? So what happens is there's a geometric argument you can use, or you can use this advanced skill called L'Hopital's rule, and you can prove that the answer is going to be 1. Basically, what this is saying is, you know, the sine of an angle theta, okay, that's not a good picture. Sine of an angle theta is basically the y coordinate of this point, right? And as it approaches 0, as theta approaches 0, the y coordinate and the theta would be approaching 0 about the same time. And that's because we are using the radian mode. And so the answer is 1. And for that one, it's probably better if you just know the answer. But you may want to review this proof of why this limit is 1. And then last one, as x approaches 0, what happens here? Well, this goes to 0, right? This goes to 0. Now, what's cosine of 0? Oh, that's going to be 1, right? In fact, from positive or -1. And so what happens is, as x approaches 0, this will go up, way up to infinity. And if x is approaching 0 from the negative side, this will approach negative infinity. So we have a classic case here where you have a vertical asymptote. And so this one actually does not exist. Okay, so that's how you can answer that question. What I should say is, well, I said this, but if you approach this, if x is approaching 0 from the positive side, okay, this is getting close to 1, and this is going to be 0, but stay positive, right? Because x is approaching 0 from the positive side. So this will go to infinity. This is what I was saying a few minutes ago. And on the other side, this will be a negative value, very close to 0, but still negative, and this will be very close to 1. And so this will be negative infinity. And because of this, we have vertical asymptote, and the limit does not exist. Now, these could be different, right? Of course, they can be different because these are the two one-sided limits. And these two one-sided limits, if they are different, then we would have to say the limit does not exist. And of course, the function is not continuous at this point. All right, let's go to number 3. Number 3 is to find the sum. And this is just a summation notation question. K goes from 0 to 5 of k squared minus k. So what is that? All right, let's look at that. Well, I'll show you a couple of ways of doing this. First, just plug in numbers. And by the way, you don't have to memorize any of these, summation formulas. There is a formula for adding, the numbers from integers from 1 to n, for instance. You don't need to know that. For this, you just have to know what the symbols are indicating. Okay, so what this means is as k goes from 0 to 5, that's 6 numbers. The first one is 0 square minus 0. Second one is 1 square minus 1. And then 2 square minus 2. Remember, all I'm doing is plugging in numbers, different numbers from 0 to 5 into k. And then 3 square minus 3. And then 4 square minus 4. And then the last one, 5 square minus 5. So that's a way to do that. Of course, that's 0, 0, 2. That's 9 minus 3. And then 16 minus 4 is 12. And the last one is going to be 20, right? And you can add them up, okay? So that's going to be 8. 8 plus 12 is 20. 20 plus 20 is 40. So that would be your answer. Now, also, you can solve it this way. K squared minus k algebraically is equivalent to k minus 1, right? So it'll be the number times that number minus 1. 1, 0, 2, 1, 3, 2, plus 4, 3, plus 5, 4. And of course, when you do that, it's 0 plus 0 plus 2 plus 6 plus 12 plus 20. And that's exactly the same as the earlier sum we found. So the answer is 40. No problem here, right? Doing okay so far? Great. I don't hear any confusion, so it must be going well. Just a moment here. Number 4 has 3 parts. Find the derivative of each, or it says differentiate, which is the same thing. So you take the derivative. This first one is a product, so you use the product rule. Remember, here's the first function, here's the second function. And the way I remember it is the derivative of a product is the derivative of the first times the second, without differentiating the second, plus first times the derivative of the second. And for the second one, you have to use the chain rule. It's going to be 2 e to the 2x, right? Now, anytime you see a same factor, it's probably best to factor that out. And so you have this, which is e to the 2x times the quantity 1 plus 2x, and that would be your derivative. Part B. All right, so you have a natural log function followed by something square. All right, before you start the differentiation process, it's best if you take that to the front, because that would make your differentiation easier. All right, remember, I haven't started differentiating yet. So now here I write f prime is equal to 2 times the derivative of this thing, which is 3x minus 1 in the denominator. And the top, you have to, again, use the chain rule, multiply this by 3. And so the top will be 6, the denominator, 3x minus 1. And that is your answer. Let's go to part C. The derivative of this, what is that? Okay, maybe you want to rewrite this. Sine to the third means you take this function and raise it to the third power. Minus 3, of course, you can sort of ignore at this point because you know it's going to be 0, right? So this will be 3 times sine 2x minus pi, this whole thing squared. That's the power rule. But again, the chain rule kicks in. You have to multiply this by the derivative of the inside function, which is cosine of 2x minus pi. But again, because this is a composition of more than one function, you have to apply the chain rule inside of this chain rule, right? And so you have to take the derivative of that, which is 2. Now, again, I would suggest that you simplify this to 6, and then you have sine 2x plus pi, and of course there's a square here, and then cosine of 2x minus pi. And that is your answer. Okay, so I'm going to pause here and then go into the next part, or the next part. Well, yeah, the next clip of the video starting number 5. This would be a good point to stop. Okay, so for number 5, look at part 2 of the series of the videos.